There's something unusual heading toward Jupiter right now. An object designated 3I Atlas is on a trajectory that will bring it extremely close to the gas giant on March 17, 2026. We're talking about zero point 0.2 astronomical units. For context, that's closer than the distance between Earth and the Sun. And it's entering Jupiter's Hill radius, the region where the planet's gravitational influence dominates. Now, I've been thinking about this object for a while. Is it just a comet? An interstellar visitor? Or could there be something more to its precise timing and trajectory? Because here's what makes this interesting. Jupiter doesn't just sit empty in space. It has dozens of moons. And some of those moons possess characteristics that scientists find genuinely intriguing. Characteristics that matter when we talk about habitability. So today, I want to take you through what makes one particular moon stand out, why its features align with what we look for when searching for life, and how an upcoming space mission might finally give us answers. Let's talk about Ganymede. Most people focus on Mars when discussing potential life in the solar system, and that makes sense. We keep finding organic compounds there, evidence that microbial life might have existed billions of years ago. But Ganymede offers something different, something that, if you step back and look at the big picture, checks two major boxes that Earth itself checks. Box 1, a magnetic field. Box 2, an oxygen-rich atmosphere. These are rare, extremely rare. Let me explain why. Ganymede is the largest moon in our solar system. It's actually bigger than the planet Mercury, and it's one of the few objects we know of that generates its own magnetic field. Mercury has one, about 1% the strength of Earth's. Venus doesn't. Earth does. Mars doesn't. Jupiter has an incredibly powerful one, as do Saturn, Uranus, and Neptune. But when it comes to moons, Ganymede is unique. It's the only moon we've confirmed with an intrinsic magnetic field. Why does this matter? Because magnetic fields act as shields. Earth's magnetic field deflects high-energy particles from the Sun, protons, alpha particles, heavier ions that would otherwise cause constant DNA damage. Without it, life as we know it would struggle to survive on the surface. Ganymede has this protection. It's weaker than Earth's, yes, but it exists. And here's where it gets visually striking. Ganymede actually experiences auroras. We've observed them. Charged particles from Jupiter's intense radiation environment interact with Ganymede's magnetic field and oxygen atmosphere, creating polar lights just like we see on Earth. Now, about that atmosphere. Ganymede's atmosphere is mostly oxygen. It also contains water vapor on the sunlit side, created when solar radiation sublimates surface ice directly into gas. But oxygen dominates. There's a catch, though. The density is incredibly low, about 100 billion times less dense than Earth's atmosphere at sea level. To picture this, Ganymede's atmosphere has a density comparable to Earth's exosphere, roughly 1,000 kilometers above our surface. So we're not talking about breathing air here. Still, the fact that oxygen exists in an unbound form is scientifically significant. Oxygen is highly reactive. On Earth, it doesn't naturally stay free in the atmosphere. Life constantly replenishes it through photosynthesis. Without life, atmospheric oxygen would quickly bond with other elements and disappear. So how does Ganymede maintain its oxygen? The current explanation is sputtering. High-energy particles from Jupiter's radiation belts strike the icy surface, splitting water molecules into hydrogen and oxygen. The hydrogen, being lighter, escapes into space. The oxygen, being heavier, lingers longer, building up into a tenuous atmosphere. That's the conventional model, and it's plausible. But here's what I find myself circling back to. On Earth, an oxygen atmosphere is a biosignature. It's a sign that something is actively maintaining an unstable condition. And while sputtering offers a perfectly valid abiotic explanation for Ganymede, I can't help but wonder if future missions might find something more complex beneath the surface. because Ganymede likely has a subsurface ocean. Evidence comes from its auroral activity. The way its auroras shift suggests a saline ocean underneath the icy crust, interacting with Jupiter's magnetic field. There's also evidence of cryovolcanism, and beneath that, a differentiated interior with a rocky mantle and an iron-rich core. So you have liquid water, a magnetic shield, and an oxygen atmosphere. Three components that, on Earth, are deeply tied to biology. Now, I want to be clear, none of this is proof of life. Speculation is just speculation, but it's worth paying attention to where our attention keeps getting directed. Which brings me back to 3I Atlas. This object flew by Mars in October 2025. It reached perihelion, its closest point to the Sun, shortly after, and now, on March 17, 2026, it performs this close approach to Jupiter, right at the edge of the planet's gravitational influence. Maybe it's just a comet following an orbit. Maybe it's an interstellar object passing through, drawing our eyes to parts of the solar system we don't usually examine this closely. But whether natural or not, its timing forces a conversation about Jupiter's moons and what they might hold. If humanity ever establishes a permanent presence beyond Earth, Ganymede checks strategic boxes: access to Trojan asteroids, proximity to the asteroid belt, a staging point for outer system missions, a position that offers influence over both inner and outer solar system resource extraction. Mars gets the headlines, but Ganymede has quiet advantages. ESA's JUICE mission, the Jupiter Icy Moons Explorer, will arrive in the Jovian system around 2031. It'll perform detailed studies of Ganymede, Europa, and Callisto, with special attention to Ganymede's atmosphere, magnetic field, and subsurface ocean. We'll finally get better data on what's really happening there. Until then, we observe, we ask questions, and we pay attention when something in the sky draws our focus to a particular place. That's all for today. I'm your host, and I'll keep following developments in our solar system and beyond. Thanks for watching. Take care of yourselves.